Before computers, drafting a mechanical blueprint required hours bent over a desk. Every line, arc, and dimension was drawn by hand through sheer physical labor. In the 1980s, computer-aided design arrived, but early CAD software mostly just digitized that exact same physical labor. You were still drawing lines one by one, just with a mouse instead of a pencil. Then, in 1986, Autodesk introduced AutoLISP. This shifted AutoCAD from a digital drawing board into a highly programmable database. AutoLISP is a dialect of Lisp, which stands for list processing. It is a programming language originally built in the late 1950s for artificial intelligence research, making it uniquely suited for handling unstructured logic. A standard CAD user interacts with the software through graphical menus, clicking buttons to draw shapes. An AutoLISP user bypasses the interface entirely to manipulate the core database directly through text commands, which raises a question. In an era of sleek, modern software, why would an engineer today spend time learning a text-based scripting language from the 1980s? Direct, because writing custom AutoLISP routines continues to reduce manual drafting tasks by up to 80%. Efficiency in digital design does not come from moving your mouse faster. It comes from writing the logic that executes the drawing for you. Consider the standard drafting loop. You navigate a ribbon menu, calculate your geometry, select a tool, draw the shape, and then assign the correct layer. This 15-step flowchart visualizes the manual workflow, with looping arrows representing repetitive menu navigation. Watch an AutoLISP routine handle the same task. The flowchart collapses into a straight two-step line. Enter starting parameters, and the script yields the final output. The main barrier to adopting this is the syntax. AutoLISP code is heavy on parentheses, which can look jarring and alienating to engineers who are naturally visual thinkers. Instead of clicking to draw a circle, you type a function block. The operator comes first, followed by the coordinates and the radius. You mathematically define the geometry in a single line of text. Learning this logic forces a temporary drop in your daily output. You will spend time troubleshooting broken code and missing parentheses instead of finishing immediate project work. This initial cognitive friction acts as a filter. It keeps the vast majority of users locked into slow, repetitive labor while masking the massive long-term productivity available to those who learn the syntax. To understand the economic value of that productivity, we have to look at AutoLISP strictly as a business investment. Take the example of XYZ Steel Detailing. Their baseline problem was simple. A drafter was spending 12 hours to complete a standard structural project using manual software tools. Rather than writing code from scratch, the firm utilized micro-automation. They downloaded free, public-domain Lisp scripts to batch process mundane tasks, like purging old layers and extracting text. This bar chart compares the timeline of the two methods. Applying those simple, pre-written scripts dropped the project time from 12 hours down to exactly 10. We can scale that 2-hour localized savings across a standard drafter's annual workload. Multiply that by a $25 per hour labor rate over 150 projects, and the compounding effect becomes clear. The result is an annual savings of $7,500 per drafter. This return vastly outweighs the cost of full software licenses or the initial training time. Micro-automation proves that you do not need to engineer complex programs from scratch to alter a firm's profit margins. Beyond simple batch processing, there is macro-automation. This is the use of AutoLISP to automatically generate complex engineering geometry from raw data. A prime example is found in the mechanical engineering sector, specifically a firm specializing in turbocharger reconditioning. Their manual baseline for this specific task was highly repetitive. It took an engineer over an hour to manually draft, layout, and annotate multi-view component drawings. They implemented a custom AutoLISP solution. This routine reads external spreadsheet data to instantly auto-generate the geometry and format the final drawings. Looking at this dual-bar timeline chart, we see the impact on administrative project setup, like folder creation and metadata indexing. A manual process that took nearly 3 hours collapses down to just 8 minutes, a 90% reduction. There is also a hidden, non-financial benefit here. Pulling data directly from a spreadsheet completely eliminates human transcription errors in the final documentation. The trade-off is steeper at this level. Macro automation requires a significant initial investment in development time and demands ongoing code maintenance as your standards evolve. At this scale, AutoLISP operates as a rigorous, enterprise-grade quality control system. IT departments often raise a valid critique. If a firm invests in automation today, why use a 40-year-old language instead of modern APIs like C# or .NET? .NET is a software framework developed by Microsoft specifically for building large-scale modern applications. This comparison matrix plots AutoLISP against .NET across 3 distinct axes: execution speed, UI support, and learning curve. Looking at the .NET column, it objectively wins in building complex, enterprise-level user interfaces and boasts blazing fast execution speeds for heavy computational tasks. But highlighting the AutoLISP column reveals its enduring advantage, a minimalist syntax. It scores vastly higher for its low learning curve, making it superior for rapid prototyping and quick, unstructured geometric problem-solving directly in the command line. AutoLISP should not be used to build sprawling enterprise software. It should be deployed exactly as intended, as a tactical, on-the-fly engineering tool. How you deploy this tool depends on your role. For the time-poor drafter, focus purely on implementation. Leverage the decades of free online scripts to fix immediate daily bottlenecks without writing a single line of code. For the CAD manager, treat code as a scalable financial asset. Invest in custom scripts to automatically enforce firm-wide standards and eliminate costly rework across your team. And for the advanced engineer, use AutoLISP to bridge the gap between raw mathematical data in your spreadsheets and the visual CAD model. Adopting this tool changes the actual nature of the work being done. The upfront friction of learning the logic is mathematically eclipsed by the decades of compounding time savings it generates. Mastering AutoLISP shifts the professional focus from manual line work toward the design of automated systems.